synthesis or meta-program synthesis.
Great, thank you. It's great to be here. And also, this talk would be slightly, I wasn't sure about the timing, so it's going to be a little free form. Feel free to ask questions in between. Yeah, and this is joint work with a lot of great interns and collaborators at Microsoft Research, and now some of the collaborators at Google Brain and DeepMind. So I think probably some of you might have seen the slide, but I still wanted to talk about it. But so one way it is an interesting way to think about progress as this we are seeing in deep learning recently, and how humans evolve. So like humans, when they're born, they start seeing the world, then they start saying things, and then they start saying things that make sense. So similarly, these learning algorithms, we've had interesting breakthroughs in vision, recognizing objects. Then we've had lots of recent successes in achieving human parity in understanding and translating speech. And recently we see new and new breakthroughs pretty much every day in language understanding. So kids nowadays, when they start to speak, after that it's very natural they start programming. So she's my 3-year-old niece writing Python programs, and it's natural we should take the progression and develop these systems to learn programming. But more seriously, a lot of breakthroughs that we've had have mostly to do with perceptual tasks, where the learning algorithm has to learn a pattern and learn some kind of pattern classifier, which is nice. It's led to many interesting breakthroughs. But when we talk about achieving general intelligence or achieving human-like intelligence, we really need to build systems that can actually learn to perform a precise sequence of tasks. And that's where we think actually programs are one good way to specify, at least represent those algorithms, because these programming languages, with programming languages we have good abstractions, and also we have the ability to compose them to perform complex tasks. So the goal was actually naturally, can we now build these systems that instead of learning these low-level matrices, they learn programs, and naturally. The hope is by doing that we'll be able to do more complex things than what we can do currently with the current set of deep learning systems. It also comes up with some interesting properties. Programs, when we learn programs, they tend to be more general. They tend to generalize better on test set because there's a strong prior coming in the design of the language. So when an expert says, okay, these are the abstractions, or this is the programming language that I would need for this task. There's some very strong prior coming in that actually tends to do better than not having any prior. And finally, there's also this notion of actually they also tend to be slightly more interpretable than just the matrices, because here if you're learning a program, somebody can go in and check if the program is what was intended, and if not, they can debug it. So there's some very nice properties of learning programs. The challenge is that programs are not as continuous as these transformations, the current nonlinear transformations of matrices. So that's the challenge. How do we consolidate those? So when we're trying to build, trying to come up with a vision, what would it take? What would it mean to measure progress towards how well we are doing on this task? One of the things that came up was can we have a challenge problem in the long term? Can we build a system that can actually program like humans, that can actually maybe win a programming contest or help anybody win these contests, or make everybody a super developer? And I'll talk briefly about some of the progress we are making there. But that's the ultimate goal, and we'll hopefully get there some point. But along the way, when we are building these models, the hope is these models would be useful for many other programming tasks. For example, they could be used for repairing programs that programmers or students are writing. They could be used for finding security bugs. They could be used for optimizing programs and many other traditional program analysis tasks. I won't go into too much detail. If in the end we have some time, we can go a little bit more there. But today I'll focus more on the learning side, synthesis side. And if we were to step back, actually, if we want to build such a system that can program like humans, I think one interesting part is we can think about how humans actually program currently. We are able to take a specification of some kind. We can take test cases. We can take maybe some natural language description. Sometimes we can take partial programs. We are able to analyze all those specification and write code. And one way to think about this is programmers need some kind of first understand what logic is needed to solve the task. So they have to do some kind of reasoning, logical reasoning. But it's not the case that everybody is super programmer to begin with. Like in the beginning, we all take courses. We start from basics. We learn. We take a lot of tutorials. Then over time, when we solve more and more programming tasks, we get better. And nowadays, actually, we leverage a lot of libraries from outside. So in the same way, actually, the idea was, can we build a system that has some similar properties, that has the capability to do logical reasoning? In the beginning, it's not going to be that great, but over time, when it has learned to solve many tasks, it will get better. Yeah. So before getting into the main part, I wanted to make a slight distinction between. I think this topic has also been quite intriguing in the machine learning community. So we've seen a lot of interesting recent papers. But I want to distinguish two major lines of work in this area. First line of work, I'll call it program induction. So I'll define what it means. So for example, at DeepMind, a couple of years back, they had this work on neural Turing machines that were extended to differentiable neural computers. The basic idea was you have an LSTM controller, and then you augment it with a memory with which you can read and write to it in a differentiable way. And then they showed that, these systems, when you give it examples lots of examples of a task, it can learn to sort arrays or copy and search, those kinds of tasks. Another very interesting paper that I really like is this paper on neural random access machines. What they do, essentially they have 14 gates, and the goal is to learn a circuit that, given some examples, it can learn to compose these gates in certain way. And the way they do it is they start with the discrete semantics of the functions, then they convert them into continuous space by defining distributions over numbers and over the operators, such that everything is now end-to-end differentiable. And then they learn, essentially the controller learns at every timestamp, every time step, what gate to use, such that the end-to-end improper examples are met. So this actually this is pretty interesting, and definitely they do add to the current set of deep learning architectures we have. They can do more things than the current systems, but they also have a lot of issues. So some of them I just mentioned here. First of all, since the one way to think about these systems is the program is the network itself. So whatever I'm training, that is my program. So when I want to test it or run it, I'll give it inputs, I'll get an output. So it's more like a black box. So they tend to not generalize very well. So I can train my DNC on arrays of size 20 up to 20, and then when I give it length 25 array, it won't sort it properly. They also require lots of examples, typically millions of examples to train. And for every task, I need to do training again. And this is definitely now not like humans learn. So this is quite different from the way humans learn, but still very promising. And there's a lot of interesting work happening there. In contrast, in program synthesis, essentially what we want, we don't want the program to be this low level matrix or these networks. We want it to be a program. We want to use the functional abstractions that we have in the programming language. And there actually the goal is to learn a program in the language. As I was saying earlier, they tend to generalize better. But it also has some limitation in the sense, let's say I want to learn a sorting algorithm, I have to train it again for every different task. And I'm still going to need lots of examples. So in this talk, I'll try to talk mostly about somewhere in between, which we call meta program synthesis, where the idea is we still want to be in the world of producing programs, but instead of requiring lots of examples, we want to learn from very few test cases, like similar to what humans do. And also, and the way we're going to get there is, instead of training different networks for every task, we're going to use some notion of meta-learning, where we're trying to do some kind of transfer. We train it on lots and lots of programming tasks, such that for other tasks, we don't need too many examples. Cool. So this was just some introduction. Now let me get into some of the more specific cases we've been looking at. So there was some application long time back, Temesa, we were working on. So this was for people who are using Excel. They might not be programmers, but they still want to get their tasks done. And in the system, the idea was people can do interesting programming tasks by giving examples instead of having to write regular expressions or macros. So here they are getting, they are able to get the name out without having to write a program. So the way the system worked internally was, there was a small programming language in the backend. Here's this most of the core part of the language. You can think of this language as a small functional language that at the top level is composition of functions. So I'm going to compose n functions, expressions, and every expression can either be a constant string or a substring based on two regular expressions. So it defines the left regular expression and right regular expression. To give an example, let's say I have this task, and one way to represent this task in our programming language would be, you want to compose 4 functions. First function is regular expression corresponding to the last word, followed by constant comma space, followed by some regular expression corresponding to the first character, followed by dot. So this would be four things, but we don't want people to write such programs. We want users to just give examples and have the system write that. So and this was something we developed some very interesting efficient algorithms to search in the space of in the space of programs. And one of the things we were thinking was, this is actually interesting because we know it's a hard problem, and it took us years to develop something interesting. Can we build a system that can learn to do such things? And out of this and some of the other work we were doing, out came more like a recipe or like a framework where this was quite useful. So at high level, the framework looks like this. We start with some programming language, let's say Flashfill DSL. And for training these systems, we're going to need some training data. And then let's assume we are able to get some training data on these tasks. We can then train our different architectures and get a synthesis system out. Now, one beautiful thing about programs, or 3 beautiful things about programs compared to, let's say, other things like images, videos, text, is that programs have well-defined syntax, they have semantics, and they are executable. And they are actually quite useful then so these properties allows us to not only generate efficiently good training data, but also during training and inference time, we can leverage these properties to do better thing than just predicting something. So just give an idea of how do we generate training data for the Flashfill task. So essentially, it's very simple. We take the language, we generate random programs. So here's a random 3-function program. It says get the third alphanumeric string, followed by get string starting from first colon, followed by get first 4 characters. So it's a random program we have sampled from the language. We generate random string, 5 strings in this case, 5 inputs. We run this program and get outputs. So this way we get 5 input, 5 output, and a program pair. We can go ahead and we can sample more complex things. Here's a program with 10 expressions, and I can run it on some inputs and get outputs. So this way we can generate as many programs as we want synthetically. We can say, here are some input-output test cases, and here's the program that I want the system to learn. Now, can anybody guess what can go wrong here? Yeah, many things can go wrong, I guess.
Special characters?
Or program might... Also, a program might segfault, yeah. So if my program says get third alphanumeric string, if I don't have alphanumeric strings in my input. So we make sure the preconditions of the programs are met. In this case, it was pretty easy because it's quite functional, so we can just gather all the preconditions and generate. But In some of the more complex languages we'll see later, it is a little bit more involved. But yeah, so the goal would be we can generate lots of training data and we can train our systems. And then to see if it has really learned the right thing, we're going to test it on real data from Excel users. So the users want to do certain tasks, can it actually learn to generate the right programs that are needed? So the hope is if it has really learned the right semantics of these things, it should be able to do well on not just on synthetic tasks, but also on real tasks. And also one interesting aspect here is that we don't give any kind of additional information. So the system from experience has to learn everything about what does 1 mean, what does number 3 mean, what does alphanumeric mean, what does colon mean. So it has to essentially learn over millions and millions of tasks to learn interpretations for these symbols. Great. So again, this is a common architecture that we found was quite useful in many tasks. So it's you can think of it more as like an encoder-decoder architecture where we'll have one module that will embed the specification, in this case our test cases examples, and then we'll have a module that will be a generative model over some language. In this case it's a tree decoder over the Flashfill language. Now so one high level way to think about what the system is doing is that we can think of our programming language as a context-free grammar. It has lots of rules, and we could do enumerative search. We could just expand all possible programs and find one that works. But these languages are very expressive, so it would take us years to find any good program. So essentially, what the network is going to do is it's going to assign probabilities to different expansions based on the base condition on the test cases users want to do. So essentially, the neural network, in some sense, is going to learn this function that will take a partial program and set of improper examples and learn how to expand the program. So there are two main challenges here. How do we represent programs in vector spaces, and how do we represent examples in vector spaces? And there are many choices. I think in the morning also we saw some interesting architectures. So we first tried out this architecture. The name is slightly scary, but it will get clearer in a bit. Essentially what it does, it takes any kind of grammar or programming language. For every rule in the grammar, for every symbol in the grammar, we have a vector representation. For every rule in the grammar, we have another vector representation. Think of them as embeddings. And then we have two sets of matrices for every rule. So from an example, what happens, let's say I want to embed this partial tree into vector space. It first does a lookup embedding for the leaf level symbols. Then it starts going up the tree. For every rule, it says, it uses the first set of matrices for every rule, let's say W, that combines the children representations and computes parents representation. This way we go all the way up. Now we can get root representation by going up the tree. This is very similar to recursive networks, what people do in natural language processing tasks. Now, but our task was actually not to just get a tree representation. We want to make decisions at the leaf level. We want to say which leaf of this partial tree looks most promising to expand. So that's where the reverse recursive part comes in. Now we do a top-down pass. We start with the root representation, and then we start using the second set of matrices for every node, for every rule, whose job is to take parents' representation and computes children's representation. So now we can go all the way down, and now we get updated set of leaf representations for every leaf node. One intuitive way also that's quite helpful way to think about this is that after doing the reverse pass, now every node in the tree knows about every other node in the tree because there's a common path via root. So information went up and went down, and theoretically at least N6 now knows about N5. So that's also a nice property. So after getting all the leaf representations, we essentially just do a dot product with possible expansions in the grammar and compute a distribution over probabilities of which nodes are most promising to expand. And since in our training data we know what the real programs are, we could just optimize the cross entropy here. And then, so we have, in this way, we have a generative model over programs. Now we want to condition it on the examples. So we want to put examples also in vector spaces. And again, there are many choices here. One choice that for this particular work was worked well was essentially what we do, we run LSTMs over the input-output strings. Then we get the hidden state representations, and we start convolving. So we try all possible alignments, do some pooling to get a fixed size vector representation for the example. And the intuition here was that in flash fill, many times the task is to find which part of output string came from which part of input string, and doing this kind of alignment might help us figure out which parts are interesting. So very briefly, this thing actually worked decently well on small programs when the programs were small, up to 13 size AST node. Gets to about 60% accuracy in the top prediction. Another beautiful thing about programs is that when you make a prediction, let's say if I'm saying this image has a cat, I can't do much about it. If there's nothing much I can do, even though it was a dog. In programs, actually, since we generate a program, we can test at least on the test cases that users provided, does it work or not. So that's what we mean here by 300 sample. We get top 300 programs and declare success if any one of them is consistent. So this was on synthetic. When we went to real benchmarks, again, similar story was there, that programs up to length 13, it did almost quite well, about 85% accuracy, but larger programs, it didn't scale well. So essentially, one of the main issues was every example had different shape of tree. So it was very difficult to put them all together to do batching, to do faster training. Especially for larger trees, the variation was much larger. So that's why we couldn't scale it up, at least at that time, a couple of years back. Now we are working on some more efficient ways to embed trees and for other applications. So then we took a step back and said, yeah, the trees are expressive, but we do lose efficiency in training. So we said, what if instead of thinking of programs as trees, what if we just make them sequences? So we can linearize the tree into a sequence. And then we can have like an architecture that says, okay, I'm going to have this seek to seek to seek model where first LSTM would embed the input. Then there would be a second LSTM that would embed the output string. And the third LSTM would produce programs as a sequence of tokens. We can add different kind of attention mechanisms. We could have double attention, and it turns out, yeah, attention helps quite a bit. Now, but we don't want to work with single examples. We have multiple examples. So the idea extends quite nicely. So we do this trick for every example that the users provided. We embed them using these two LSTMs. And then we get a latent representation of programs for every example. And we do some kind of max pooling to come up with a program that is consistent with all examples. And the assumption is it's doing some kind of intersect operator where we want programs to work well for every example. And the nice thing about this architecture is that since it's all sequence-based, we can easily batch them. We can parallelize training on lots of GPUs. And since it was working so well on the original DSL, we went ahead and added even new constructs here, all kinds of new things that we previously couldn't add in FlashFill because previously it was very painful to add anything new. It breaks all the assumptions on the algorithms. But now, for this case, we just add new things to our language, and we just get more training data and train the system. And one of the interesting parts here was that once we tested the system on the real examples, it gets about 92% generalization accuracy, which was even better than the 89% that the handwritten algorithm got after several years of work. So that was actually one of the most interesting things we found, that actually these architectures are able to learn the right abstractions and perform some very complicated search just from training. Another nice property of these things is that they're also robust to noise. So if people make mistakes in spellings or something, since the FlashFill algorithm was sound, it would either say I can't find a program, or it will give me a very weird program that says, yeah, some complicated thing. Here actually it degrades quite nicely. Even if we have 4 or 5 characters of mistakes, it still is able to learn the right program. And whenever it makes mistakes, we were looking at cases where actually it couldn't get it right. It was kind of intuitive why it didn't get it right. So for example, in this case, the top 4 are the examples that we gave it to the system. And the system learned that the program is get first 2 digits, which is fine for the examples. But it turns out in the test set or in the held out examples, there was few numbers that had more than 2 digits. So the right thing there to learn was get first number, but it kind of makes sense, like even if it learned to do 2 digits. So because of time, I will skip this part, but I'll go into some more interesting parts. So I think the flash fill experiment gave us some interesting hope that I think these techniques are doing something really interesting. So we wanted to see can we now extend how well these techniques work on more complex languages. So flash fill was nice in the sense it's a small functional language, but still it didn't have control flow, it didn't have loops, conditions, variables. So Carol we'll see briefly. It has slightly more complex constructs. Then we are also looking at more full-fledged languages where they also, so Carol doesn't have variables, so Python and R scripts for data transformations that also have variables. And then there's also some interesting work we're looking at just from the theory side. So we know that these networks or even 2-layer feed-forward network is Turing complete, but to train and expressiveness and learnability are 2 different things. So the question is, what kind of languages can we learn? And from the specification side, I showed you examples, example-based specification. There's also some interesting work on the nice thing about these neural models is if I have a natural language description, it's just another encoder for me. I don't have to rewrite my full system. So there's some work on generating SQL programs and Excel programs from natural language and partial programs. So there's some interesting extensions here. I'll briefly talk about Carol, and then over the break I can talk about other things if people are interested. So Carol, as I was saying, it's another interesting language where there's a robot whose name is Carol, and they have to move in this 2D grid world where they can put marker, pick markers. So for example, here for this case, a program that does a transformation involves a small loop that does 4 put marker operations and turns left. Interesting part about this language was that first it has some control flow. Secondly, it's taught at Stanford, so it was something like a test case for us. We wanted to see how well it does compared to students who are also taking this class from scratch. They also don't have too much programming experience, but over time they are able to learn this programming. So that was another interesting aspect. So the language has certain actions, but the interesting part is it has loops and conditions, and they could have nested things. So as I was saying earlier, the framework was very similar. We generated data sets in a similar way, but here it was more involved because since we have loops and conditions, it wasn't as straightforward to generate preconditions, but with some work we can do that. And the architecture was kind of similar. The only difference was instead of using LSTM-based encoders, we were using CNNs because the hope was that these images have certain interesting properties that the network can learn. Do I need to use a loop, or what kind of loop pattern do I need to use? Looking at these visual diagrams. Yeah, so doing similar thing, actually it works reasonably well. On synthetic data, it gets about 70% accuracy. One of the problems, more generally in the supervised approach of learning, is that when we do program example, there can be multiple programs that are consistent. So here I have 2 programs A and B that probably do the same thing, or maybe not, but the idea is there can be multiple programs, and we are penalizing during training the system. Even if it comes up with a good program, we say no, make sure you only produce the program that I gave you during training, even though it's okay to have any program that has the right semantics. So the problem is to train such an objective function, we can't use supervised learning because we need to execute the program, and that is non-differentiable. So that's where a little bit of reinforcement learning came up. the idea was, and also we can't do it from scratch because the rewards are very sparse. So if we start from scratch, we would never get any reward in 300,000 iterations. So the high-level idea was we first do supervised learning. We get a reasonable model to begin with. Then we start sampling programs for new test cases, and then we get a family of programs. We run all of them, and depending on how many of them are correct on a test case, we give positive reward. We give +1 if it's correct, 0 if it's incorrect. And it turns out actually doing this kind of small reinforcement learning on top of this supervised learning, it was able to solve about 6 to 7% more. So then this was on synthetic data sets. We also took the class test from last year at Stanford class, which had 16 problems. All of them were of the same form. They have input outputs, and students have to write programs. And it turns out actually I was expecting 0% here, but it was able to get 7 problems right, which was quite again surprising. One of the programs that it got right in the class was this slightly complex program. It's able to write this program that is able to do this complex operation. Yeah, so essentially the goal now is to improve this and get it to 100%, similar to how students, actually most of the students are able to solve all the problems. And then there's some recent approaches on how to not just do completely neural, but add more symbolic reasoning, sketching-like approaches to guide the search. Great, how much time is remaining?
15 minutes plus with questions.
Oh, great. So maybe I'll try to finish it up in 2 minutes. So as I was telling that, yeah, I think there's lot of interesting ideas here to do program generation, but along the way, the embeddings we are developing could be useful for other tasks. So one of those tasks we have been looking at is fuzzing. Fuzzing is this very simple idea. You have some binary you want to test, and the idea is you just do random inputs and you find anyone that crashes. Now you have a certificate that I have an input that crashes. And it works really well. It's being used to find several real world crashes. Now this technique works well when the inputs don't have too much structure. So if I have an image, I can just randomly perturb pixels. But if I have a PDF file or an XML file, if I randomly make changes, very quickly it will become invalid. So the idea here was, can we use some of these generative models to learn some notion of grammar? So we give it lots of PDF files and ask it to generate new PDF files, somehow learn the structure of the PDF document, or in this case objects, such that when we're generating new inputs, they're not trivially invalid. And it turns out actually these systems can learn some notion of grammars, and they can lead to more coverage. Similarly, this was more like I would say more like an AlphaGo style approach, where let's say I have this random fuzzer. It's trying to mutate bytes, and then it's getting reward whenever I get new coverage. So in this case, we had some PNG file. We started making random mutations in the beginning, and then seeing the reward. Am I getting to new places in code? Am I observing new crashes or not? And then over time, by giving this kind of reward, that whenever it gets to new paths, we give it high reward. Whenever it goes to the same path, we say don't go there. Over time, it can learn a structure, a policy over which inputs in the bytes are more important to fuzz. And when we visualize it back, it turns out it seems quite a bit like a grammar of PNG file, which was also quite interesting. And it found many more crashes than the state-of-the-art AFL fuzzer. Yeah. And finally, another cool application domain was this thing about program repairs. In this context of students, here these were programs that students were submitting on online courses, MOOCs courses, where they're all trying to solve the same problem, but they all make different kinds of mistakes, and we don't have enough manual teachers to give each one of them good feedback. So the high-level idea here was, can we learn these program embeddings, these code models that can learn to represent correct programs for any given problem, such that when an incorrect submission comes in, these models can pinpoint, I think there's something wrong here, and then give suggestions on how to improve or how to correct the programs. And there's some very interesting ideas on how to embed these programs using both syntactic and dynamic traces. So just to conclude, I think there's some really interesting, actually, yeah, I think with recent advances in current, both in learning techniques and symbolic solving techniques and the computational hardware, I think this is really good time to now explore these kinds of large search problems, and program synthesis is in some sense one of these giant search problems, but that also ties in very well to one of the most fundamental intelligence problems. So the goal is to build a system that can actually understand test cases, examples, programs, and the long-term vision is to build a system that can do as well as humans, but along the way there are many applications that can be enabled by building such systems. So thank you.
We have about 7 minutes for questions. So.
Great. Yeah.
It's really nice talk. So the example that you give for concatenation, or you had an empty image, you want to go to a different position.
Yeah.
It looks like quite planning. So you want to learn a fixed plan given some input.
Yeah.
And you change the input, but the plan is same. You have to
Yeah.
continue the same plan. So it's
Yeah.
really nice. So I guess existing ILP models can't do that. They will learn a set approach, but yeah, it's nice to see these things coming.
Yeah, so actually didn't talk about, we tried many existing systems also on this problem. So sketching is one which does SMT based solving. We tried some variation of answer set programming and those kind of things. Yeah, and those, they don't scale to these tasks. Yeah.
Yeah, really nice to see actually.
Yeah.
It's nice progress.
Great, thanks. Yeah. Hey.
So clearly for cases where you don't have a formal specification, I think like the spreadsheet macros, there I think it's a learning problem fundamentally, and this is sort of a natural approach. But what about the cases where you want your synthesized program to satisfy some formal specification, partial or complete? Do you think approaches like neural program synthesis can be better than something that's based on symbolic methods like sketch?
Yeah. No, that's a wonderful question actually, and that's something we keep discussing quite a bit. We haven't yet tried anything, but one couple of ways we've been thinking to integrate such strong specifications in this loop is more in the reinforcement learning setting, where we give it really high penalty if it ever violates any of the strong guarantees we want the final program to achieve. So that's one very simple and naive way to add such a thing. But in more supervised case, I didn't talk about, there was a paper last year at NIPS where we showed that since programs can be executed, what you do, you have your LSTM predictor program. Now you execute that program in a non-differentiable way. You get some output, and then you can do a little bit of back propagation after that to do small amount of meta learning. So these kinds of constraints can go there as well. So once there's a generative model, you sample a program, you check what kind of properties it does it satisfy or not, and that information can go back to the encoder.
Program on the given test suite?
So that was still on the test suite, yeah. But one can imagine adding other constraints, yeah, at the test time. But it won't be used directly in the first encoding phase. It would be used more as a feedback mechanism, yeah. But yeah, I think that's a wonderful problem, and we haven't yet looked too much into it. Some high-level ideas we were discussing, yeah. Yes.
Yes, in your abstract, you touched on kind of connection between AGI and some of this. And I think you alluded to it once or twice in the talk. I thought that was a really interesting connection. I haven't really heard made before, but actually I find it convincing. I just wondered if you wanted to elaborate.
Oh yeah, didn't talk about it much. And actually that's one of the reasons also why we are seeing such a surge in both papers and people working on this in the machine learning community as well. Yeah, the connection is more like when we can think of programs as in some sense the purest form of computation. Like we can express many interesting things there. So one way to think about programs is that if you think about SVMs or linear regression is a single line program. SVM is, or maybe decision trees are these bunch of if-then else's. Neural network is this nonlinear sequence of transformations. So they're all like very specialized class of programs. But if we are able to learn general arbitrary programs, then we can encompass all of the specialized class of learning that is happening today. So the one aspect is there that we could now train systems that can go beyond, not just beyond things that are possible today, but do arbitrary computations. So that's why people think that actually if we were to solve this problem, we will actually move towards more general intelligence.
I know some cognitive scientists have kind of argued that language is like a kind of tool for organizing our own thoughts. So that seems to be connected.
Yeah, there's that connection as well, like similar to like humans. So there's that connection as well. Like humans don't think in terms of low-level neurons. They have these abstract concepts, and they learn when to use which concept and how to combine. And again, programs gives us this vocabulary to identify these abstractions and join them in different ways. So actually, there's some very interesting cognitive science papers as well recently on using program induction to identify how children's react to certain observations. Yeah. Great. Yes.
You mentioned using reinforcement learning, and I sort of know in the general reinforcement learning community, we've got a bit of a reproducibility crisis, and these models are known to be incredibly sensitive to various parameters and random seeds and so on. I was just wondering, did you find that to be the case for the stuff you were working on? Was it basically pretty okay?
Yeah, so as I mentioned, actually we weren't starting from scratch. So yeah, I think we did try lots of experiments. We spent almost a month doing that, and turned out since the space is so large, when you do multiple rollouts, you would never get any reward. So even 3,000 iterations, we try to find single program that works. It's too big a space. So what we were doing was we first train a supervised model based on the training data. Then we start doing small perturbations to the distribution on top of that. So we did try multiple times, and maybe because we were starting from a good starting point, it didn't really affect that much. Like the initialization was almost fixed. But yeah, in more general sense, if we were to do from scratch, then there would be very interesting problems. Oh, yes.
Do you support constants inside your DSL?
Yes. So the Flashwheel example I was showing, but those are limited constants in the sense it would say 5th alphanumeric or 10th character. So they come from a fixed vocabulary, because we were in this case we were just trying to learn probabilities over grammar, and the grammar has to be fixed. In the follow-up ICML paper, we were generating programs as sequence of tokens. So there actually we don't really care. We just do ASCII characters. So there it's okay to generate arbitrary integers as well. Yeah.
I think we're out of time. Sorry.
Oh, we can discuss afterwards.
Yeah.
Thanks a lot. Yeah.
Thanks.